Hello, Year 10s. This is a recorded lesson that I'm recording before our opening to school, and it's just basically a simple review on electrolysis. As I mentioned in classes, you guys have had lots of lessons on electrolysis and different types of electrolysis, so you guys can kind of assume that this is going to be a topic that you are going to be tested on quite frequently, as well as it's something that you need to know quite well before you move on. Okay, so the first things that we're going to look at is basically what makes electrolysis work, and then afterwards we're going to be talking about the actual process of electrolysis and how it works. And then we're also looking at specific examples like we did in lessons 11, 12, and 13 at different situations. But I'm going to try and do a better job of trying to encapsulate everything that goes on in those lessons. Okay. At the end of this lesson, there's a worksheet for you guys to work through. So you can find that on your class Teams page. And then you can either work on that while you're going through this or watch this first and then do the problems. Okay. Whichever one works for you. All right, so let's get started here. So the first thing that we need to understand about electrolysis, right, is how does it actually work? Okay, and I throw this term ion around a lot, okay, but it's actually really important. So ionic substances contain, contain charged particles, right? And those charged particles are what we call ions. So that word ions is actually going to be very, very important. Okay. For example, okay, if I have a solution or I have an ionic compound called sodium chloride, okay, sodium chloride has the formula NaCl, right? Because it has sodium and chloride. Now, if I broke apart the two elements that make this up, I'm looking at sodium and I'm looking at chloride. And you might be thinking, well, how do I know which one's which? And by that, I mean which one is positive and which one is negative. You have to look at your periodic table. Okay. Now, looking at this periodic table, okay, I've already kind of drawn on this, but you can see sodium is over here and chlorine is over here. Okay. Now, between the two, okay, all atoms or all elements want to become stable. And in the periodic table, there's only a group of elements that are considered stable, and that's these ones over here in group 0. Okay, so these group 0 elements, okay, let me just scroll this up a little bit. So these group 0 elements, helium, neon, argon, krypton, are all stable because they have a full valence shell. All right, so if you are unfamiliar with valence shells, you definitely need to go back and review that because you need to understand that before you move on. So these all have full valence shells, whereas things like chlorine, okay, chlorine is in group 7, which means I told you guys before that if it's in this group 7, then it has 7 valence shells, okay? And the magic numbers that you need to memorize is 2, 8, and 8, right? And that just represents the max number of electrons that fits in each shell, okay? So chlorine has a total of 17 electrons, which means that it has 2, 8, so that's 10, and then another 7, which means that it's one away from having that full third shell. Okay, so where's it going to get its electron from? Well, sodium on the opposite end is in group 1. So that means that sodium has one valence shell. Okay, so sodium would want to give up that one valence shell to then have just 10 electrons, right? So your magic numbers are basically 2, 10, 18, 36, and whichever one it's closer to, that's the one it's going to try and get to. So 17 is pretty close to 18, just need to add an electron. 11 is pretty close to 10, so it just needs to get rid of one. And that's how it works, okay? Now, electrons carry a negative charge, right? So sodium, okay, if it loses that electron, then it becomes a positive ion. Okay, so in this one, our sodium is plus, and our chlorine gains an electron, so it gains another negative charge, which means that chlorine becomes minus. Okay, I can show you the ions for these ones as well. So oxygen, right? Oxygen wants to gain 2 electrons rather than losing, what, 6, right? So it's much easier for oxygen to gain 2 electrons. So if oxygen becomes an ion, it becomes 2 minus. Okay. Now, just by itself, it's pretty simple. But if you have, say, for example, copper oxide, CuO, okay? If I told you that's the formula for copper oxide, and I asked you, tell me the charges on each of these, it's actually not that difficult because you might not know what copper is because copper is kind of in the middle and it doesn't really have a group, right? But you know that oxygen is 2 minus, okay? So whatever copper is, it has to negate that 2 minus, has to balance it out, just like how the plus and the minus balance each other out. So then copper becomes 2 plus. Okay? So then these are pretty simple ones. What happens if I get one that is a little bit unbalanced? So say, for example, let's say magnesium chloride. So magnesium is here and chlorine is here. Okay? So MgCl. Now, right off the bat, there's something wrong here because magnesium is in group 2, which means that it's going to lose 2 electrons. So right off the bat, we can say Mg2 plus. But chlorine, okay, doesn't need 2 electrons, it only needs 1. So chlorine is actually just a minus, right? These don't balance out. So what we need to do is we actually need to have 2 chlorine atoms attached to this magnesium. So what happens is now I have 2 chlorines that both 1 electron each. That gives me a total of 2 electrons that need to be obtained from somewhere, and those 2 are going to come from magnesium. Okay? This is all going to become important with electrolysis, okay? I promise. All right, so that kind of explains the whole bit about ions and how, in electrolysis you need to have compounds, right, or solutions that have positive and negative charges. Okay, so let's actually define the term electrolysis here. Okay, so electrolysis is the process by which ionic compounds such as sodium chloride or magnesium chloride compounds are broken apart, broken down into simpler substances when a current, or I should say when an electric current, got to be specific here, is passed through. I know that's a really long definition there, but that's probably the longest thing that you might have to write today, okay? So there's your new term that you need to understand there is electrolysis, okay? So in a nutshell, what we're doing is compounds like sodium chloride, magnesium chloride, and copper oxide, all we're doing is we're just basically breaking apart into its 2 separate elements. So sodium chloride becomes sodium and chlorine. Magnesium chlorine becomes magnesium and chlorine. Copper oxide becomes copper and oxygen, right? And we're basically breaking it down into its 2 simple elements. And just to give you an idea of what that looks like, sodium chloride, if you guys don't know this, sodium chloride is salt, right? I've been mentioning this many, many times. So that's normally salt, sodium chloride. But if I broke it down into its 2 separate forms, sodium is actually a metal and chlorine is actually an acidic gas. Okay? And so you would never think that the salt that you have sitting in your kitchen right now is actually a metal and a gas put together. Okay? But that's what can happen when you put things through electrolysis. All right, so let's kind of speed up the pace here, okay? Electricity, as we know, is the flow of electrons. And for electrolysis to work, the compound has to contain these ions. If it doesn't have ions, so say, for example, if it's a covalent bond or a covalent compound, which means that electrons are shared, not donated and accepted, then it's not going to work. So it has to be an ionic compound, okay? And the last thing that must happen, right, is that these ions, okay, so this is a little catch here, okay, ions must be free to move around, okay? And so there's two ways that you can achieve this, okay? There's two ways that you can achieve this. One, let me just do this in a different color because it's really important. So one, you can either melt it or dissolve it in water. Those are your two ways that you're going to be able to do this, okay? Now, these two forms are actually very similar, okay? Bottom line is they're both liquid, okay, or aqueous, I should say. So this is technically a liquid, that's technically aqueous, but it doesn't really matter because the only difference between the two is this has water, this doesn't, okay? But they both behave like a liquid, okay? Aqueous just means that it has water or it is dissolved in water. Okay, so we've kind of set up the stage for electrolysis to work. We have an ionic compound and the whatever that we're trying to break apart, so sodium chloride, magnesium chloride, whatever it is that we're trying to break apart, we have it either melted or we have it dissolved in water. Okay, so let's kind of draw out the basics of electrolysis. So electrolysis have several components that are very, very important. Okay, and here are the components. So we have a battery. We have two electrodes. And then last thing is we have electrolyte. Okay. So I'm just going to be very straightforward here because obviously this is something, if you attended the lessons, this is something that you learned as you went along. Okay. Now, your electrodes are very important because they will tell you where the ions will go. So on this end, we have a negative ion, or sorry, negative electrode, and here we have a positive electrode. Now you might be thinking, how do I know that? How did you just decide that? Or is it random? It's not. This diagram right here, okay, this is, if you remember back on your electricity unit, this is the diagram for a battery. So this is your negative side, okay, and that's your positive side of the diagram. So that's why this is negative and plus. Now these have names. The positive side is called your anode. The negative side is called your cathode. All right, and it's just basically charged. So basically you have electrons, okay, that are moving like this. So electrons we denote with an E, kind of like to the power of minus, if that makes sense. So your electrons are moving like this. Okay. Now these electrons have to come from somewhere, but we'll get to that in a second. So the current is kind of moving like this. And since this is a ionic compound, it can actually conduct electricity. Okay. So this is our kind of our circuit right here, our circle. Now, our positively charged ions are going to be attracted to the electrode here, okay? And then our negatively charged electrodes are going to be attracted here to the anode, all right? Let me explain that. So here, this little liquid that I have, this is called my electrolyte, okay? And this contains ions. So whether it's sodium chloride, whether it's magnesium chloride or copper oxide, it just contains all of those sodium chloride. So what's happening here is, let me just use these colors here. I basically have ions of Na plus, Na plus, Na plus, Cl minus, Cl minus. And if I was able to animate this, this would really, really help, okay? So imagine I got billions of these little small ions in this solution here, okay? Now, before you draw that, I want you to stop, okay? Because I'm gonna move these around. Now, you guys know if you've ever played with magnets, right? You have a negative side and a positive side. And if you put them together, they get attracted to each other, right? And then negative and negative, they repel each other. Same thing applies here, okay? So my positive ions are going to go to the negative ion, or sorry, negative electrode. And my negative ones are going to go to over there, all right? So then, and then this is why I wish I could animate this. So basically what I have is I have a bunch of ions that are being attracted and quite frankly separated, okay? So my Na was over here, and I'm just gonna, because I want to fit as many as I possibly can. And then over here I have Cl minus, Cl minus, Cl minus. Okay. It's important to note that because this is a liquid, you're still going to have chlorine atoms over here because it's just too far away, right? And you're going to, same thing, you're going to have sodium ions probably over here that don't get attracted to this, they just get repelled. Okay, so they're just kind of stuck over here and they won't really make it over there. All right. So here we actually have electrons being transferred now. Okay. So this is what's happening at each end. So at the anode, okay, at the positive electrode, we have chlorine, which is basically giving up these electrons, okay? Because these electrons have to come from somewhere, right? And chlorine is Cl minus, which means it has an extra electron than what it's usually having. So chlorine, okay, chlorine Cl minus will, well, we'll say lose an electron. Lose an electron. And when it loses electrons, it actually combines with you. So let's say, for example, this Cl minus and this Cl minus, they both give an electron and they find each other actually, and they will bond with each other. And so that forms two chlorine atoms put together, creates Cl2, which is a gas, chlorine gas. All right. On the opposite end, sodium, so Na plus will gain an electron from here. So this electron that the chlorine's donated is going to travel all the way across and it's going to land up at this negative electrode where the sodium are all collected now, and Na will gain an electron and form Na, just Na, not Na plus. So sodium by itself, neutral, without a charge, is just sodium metal. Okay? So that's kind of how you will find out what's happening to the electrons, right? This part is important, is the actual transfer of electrons, okay? The chlorine and the sodium, however, all right, we actually have a name for what's happening here, all right? So the name that's happening, if something loses an electron, we call that oxidation, right? So at the anode, you can bet, all right, and this applies to everything. Every electrolysis example. At the anode, you have oxidation happening, okay? Because whatever's forming at the anode is going to be a negative ion, and so they will always give up their electrons, and so they will always be oxidized. Whereas at the negative electrode, so at the cathode, electrons are always being given, okay? And if something gains electrons, we call that reduction. And again, in one of the previous lessons, okay, prior to this, you guys learned that a way to memorize which one's which is the mnemonic oil rig, right? So oil rig, I'm just going to write it down really quickly here. Okay, oil rig just basically stands for oxidation is loss, reduction is gain, and that's referring to the electrons that are being passed around. All right. And then from here, really, it's just a matter of memorizing all. So basically, what's an electrolyte, what's anode, what's cathode. And so the mnemonic that you're going to use here to memorize this, okay, is panic. Okay, which is kind of funny because I don't want you to panic. All right, but you know, the tool is still there. Okay, so for panic, it basically means positive anode. Okay, because the anode is a positive electrode. Okay, and then NiC or Nic is negative, is cathode. Okay, and that's how you're going to memorize. That's how you're going to memorize this. Okay. So if you want to go ahead and pause that video and really quickly just copy that down. I'm going to go on, okay, because I want to make sure that this fits in. And what we're going to do is we're going to go over several examples of different types of electrolysis, because that was basically what happened in the next portion. So in lessons 11, 12, and 13, we looked at specific examples of electrolysis of different metals, different ionic compounds. And this is actually really important for you guys to memorize. And so I'm going to start with the easiest one because I always like starting with the easy ones first, okay? All right, so running on borrowed time here, so I'm just going to go as fast as I can to make sure that everything fits in nice and neat. So there's three ways that electrolysis can be used, okay? The three ways are you can electrolyze molten salts, ionic solutions, okay? Specifically aqueous, and you can also do something that's called electroplating. Now this one I'm not actually too concerned about. If you did attend the lessons, electroplating was actually when we were discussing the purification of copper. Okay, so this one I'm not too concerned about. These two are the ones that you absolutely need to know. Okay, so the examples that I'm going to use for this one is lead bromide, and then this one was the electrolysis of brine. So these are the examples that I used in class. I'm going to quickly go over them again, and then I'll give you guys more examples that kind of go on top of this, okay? So let's look at molten salts first. Oh, sorry, I meant to say molten salt. That's what I meant to say. Okay. All right, so lead bromide. So this one is easy to predict the products of electrolysis because they basically just split into their elements. So lead bromide has a formula PbBr. Okay, and I think this one. So bromine is one. So this is actually Br2, and this will form lead and bromine gas. That's it. Okay, that's the formula for what's going to happen. Now, these ones are quite simple because if I quickly drew what was happening again, so if I have the battery, electrode, electrolyte. So here, my electrolyte is going to be lead bromide. So what I've done, or what I would do, is if I have lead bromide, which is basically just a substance, and I melted it hot enough so that it becomes a liquid, okay? Then I put that liquid into here, and then I turn on the battery and the electricity is running through, right? So again, this is my positive, this is my negative, that means this is my anode, and this is my cathode, right? All right. Now, before I do anything, I have to determine the ions for this, okay? So my ions are going to be as such. Looking at your periodic table, right, do the ones that you know first, okay? Lead is over here, okay? It's in group 4, and it's all the way down there. So you can kind of guess that it might not behave the way that you expect it to. But something like bromine, right, is far enough up on the periodic table, and it's in group 7, so you know exactly how it's going to behave. It is looking for one electron. So bromine, if it becomes an ion, is going to become Br minus, okay? And that's why we have two bromines. So that means that if I have two Br minuses, I have a total charge of 2 minus. That means my lead has to be Pb2 plus. Okay. So now I have my charges, and now I can tell you that my positive ions are going to go to my negative, and my negative ions are going to go to my positive electrodes. So I'm going to write Pb2 plus PB2 plus P, and obviously you might want to draw this a little bit bigger. Okay, just try and make it as neat as possible. And same thing, right? I have my electrons, okay, that are moving from here all the way around to that side. And so what I'm going to get is bromine gas. Okay, so these are going to give up their electrons. I'm going to get bromine gas, which is Br2. And then on here, I'm going to get lead Pb, just regular Pb. Okay. And again, same thing, guys. Okay. If something is losing electrons here, right, the bromine at the anode is being oxidized. And this is really important because you're going to get questions like this, right? What's happening at the anode? And the answer to that is it's being oxidized. And at the cathode, you're being reduced. Okay. And if you're thinking, well, why is it reduced? It's because it's gaining electrons from this entire current that's running around. Okay. So these lead ions, right, they're missing 2 electrons because they technically, when this is happening, right, when it's in solution like this, even though the ions are separated, they're still the electrons are still there, right? They're still being donated and accepted. So lead already gave up 2 electrons to 2 bromine atoms, okay? And then those ions are basically going to be transferred back, and it's kind of like we're forcing those electrons back into lead to shape back into regular, just solid lead. All right. So molten salt like this is pretty easy because all we're doing is we're just separating a solution into its 2 basic elements. All right. Now, another trick that you can use in this one is that at your negative electrode, okay, here, it's always going to be, if it's a molten salt, you're generally going to have a metal that's formed. Okay. And then over here at your anode, you're going to have a non-metal, which is formed. Okay. And this is just because, let me just quickly explain this here. All this time we've been talking about ionic solutions. Okay. Ionic bonds or ionic compounds are generally formed between a metal and a non-metal, which is why when we separate it, you will get a metal and a non-metal. And this kind of trick tells you that at the cathode, you're always going to get the metal, and at the anode, you're always going to get the non-metal. And in this case, lead, as we know, is a metal, so the lead is going to be formed at the cathode, and the non-metal in this case is bromine, and bromine is formed at the anode. Okay, so just a simple trick that you can use to kind of memorize, well, I don't remember anything else, but I do remember that metal is formed at the cathode. Okay, and you kind of work your way backwards in that sense. Okay, so go ahead and pause the video if you need this section right here, but I'm going to move along and we're going to be talking about ionic solutions. Now, this one is a little bit more difficult to understand. In the lesson, we talked about the ionic solution of brine. Now, brine is a simple way of saying salt water. Okay, so it's nothing too crazy, but the actual things that's going on is okay. So same thing. Actually, sorry, I'm just gonna move this across because I just realized I'm moving slightly towards the left here, and I don't want to make this video too long, so I'm aware of how much time I'm taking here. For those of you who have done this and this is making a lot of sense for you, and what you can do is while I'm going through this, you can go through the questions. All right. So this one has a lot more rules attached to it. Okay. So what I'm going to do is I'm going to show you the what's going to happen if I have a solution of brine, which is salt water, right? So that is Na plus and Cl minus and water. Okay, now water is kind of special because water can dissociate, which means break apart into 2 separate ions. Now water, is H2O, right? So 2 hydrogens, 1 oxygen. Those can break apart into 2 ions called hydrogen and hydroxide. But the formula is still there, right? I have 2 hydrogens and 1 oxygen. Okay, so these are actually my 4 ions that are going to form if I electrolyze brine or salt water. But the same principle applies. My positives are going to go to my cathode, and my negatives are going to form at my anode. Okay. So if I drew this out, I'm going to have hydrogen plus, hydrogen plus, hydrogen plus, and OH minus, OH minus, OH minus. And then my salts, right? So Cl minus, Cl minus, Cl minus, Na, so Na plus, Na plus, Na plus, right? And this is what happens. My ions, regardless of what they are still going to be attracted to whatever electrode they're being attracted to, okay? In this case, opposites. So in this case, I like to look at each electrode at a time, and that way you kind of get a sense of what's happening. So here, okay, the key phrase I want you to know here is that whatever is produced, okay, so metal ions and hydrogen ions are positively charged, right? as you can see here. And whether you get the metal or the hydrogen depends on the position of the metal in the reactivity series. So this is where you have to pull out this dandy little chart right here. Okay, so we're looking at sodium and hydrogen. Okay, sodium and hydrogen. And the rule is the metal will be produced if it is less reactive than hydrogen. If it's not, then hydrogen will be produced if the metal is more reactive. So let's say in this case, I'm going to write down the rule for this case here. And I'll actually write this in black, okay? So hydrogen will be produced if the metal is more reactive. Okay, so looking at this, sodium is much more reactive than hydrogen. That means that hydrogen will be produced, okay? So at the cathode, H2 is produced. Okay, that's that. Nothing more complicated, okay? And I'll show you examples of where hydrogen is not produced, okay? And the rule of this comes off of the fact that more reactive metals or more reactive metals tend to stay as ions because they already are in a bond with the opposite, right? So in this case, sodium is bonded with chlorine. Even though the ions are freely floating around, they're still technically bonded because the electrons have been donated. And so they like to stay like that, okay? They don't want to move around. On the opposite end, okay, we have another rule, okay? And you might hate me for this, okay? But if the negative ion from the ionic compound is a halogen, okay? Then that will form as a gas. But then if there's no halogens, oxygen will form. Okay, so that's the rule here. Okay, and you might be thinking, well, how do I know what a halogen is? You never told me this. Simple. Halogens are anything in group 7. So fluorine, chlorine, bromine, or iodine. Any one of those 4, if it appears on your solution, then that's what's going to form. Okay. So in this case, we have chlorine and hydroxide. Chlorine is a halogen, which means that chlorine gas will be formed. Okay. Now that kind of leaves a question of, well, what about everything else? What about the sodium that's just sitting around? What about the hydroxide? Well, fear not, they will be used. Okay. So the last thing is that everything that's left behind, okay, so these will combine to create the third product. So in this case, NaOH is produced. Okay. And this will happen more than often because in a situation like this ionic solution, you will generally have 2 types of ions at each electrode. And then whatever's not used up will combine to create a third product. Okay, so in real life, this would look like hydrogen gas, so bubbles forming at this one, and then chlorine gas, so bubbles forming on that one. And then if I got some litmus paper, or if I got a universal indicator and I dropped it in here, NaOH, or sodium hydroxide, is alkaline, so this would turn purple if I did universal indicator, or it would turn, actually, yeah, it would be purple on litmus paper as well. Okay, so let me give you an example of where things might change around, okay? And I'm going to try and squeeze it in here because I want to use this as an example, okay? So in this case, if I have, for example, copper chloride, so CuCl2, right, and water, so that's in water, okay? So then my 4 ions from this would be, again, chlorine is minus, all right, which means that Cu has to be plus, but I have 2 of them, so that has to be Cu2 plus, and then hydrogen and oxygen will dissociate, or water will dissociate into hydrogen and oxygen. So then what I'm going to do is I'm going to take all the ions from here and I'm going to separate into pluses and minuses, okay? So my pluses are going to be Cu2 plus, right? And hydrogen plus. Okay, just like how I did it up here. I got my metal and my hydrogen. On the negative side, I have chlorine, okay, and OH minus, right? Just like how I did it up here. So then the question might be, what's going to be formed at the cathode and the anode, okay? So let's look at the cathode first, because we did that first, right? So it says that hydrogen will be produced if the metal is more reactive, I didn't finish this here, than hydrogen. Okay, sorry about that. I realize that probably would have made more sense. So hydrogen will be produced if the metal is more reactive than hydrogen. Okay, so looking at my reactivity series, all right, copper and hydrogen. Copper is below hydrogen, so copper is less reactive, which means that hydrogen is not going to be produced, right? It's actually going to be the metal. So in this case, I'm going to get copper that's formed. Okay. So I think I failed to mention that here. So hydrogen will be produced if the metal is more reactive, but in the case that it's not more reactive, then you're going to have the metal that's formed. Okay, and in this case, copper is going to form a metal, not copper gas. So you're going to have copper that's forming on the electrode itself. Let's look at the anode here. So I have chlorine and hydroxide, which is exactly what I have in the example that I put up here. So in this case, I don't really need to talk about it because chlorine is in group 7, or it's a halogen. So if it's a halogen, then it will form. So in this case, my chlorine gas will form. Okay. Now this is very broken because obviously if I had to write this out, I would say, copper is formed, chlorine gas is formed, and I'd actually say Cl2 and just Cu, not Cu2 plus. Okay. But that's what your answer would look like. Okay. If the question was something like what's going to form at each of these electrodes here. All right. And I think that's kind of where I want to leave things. All right. The last thing, like I said earlier, was electroplating. But like I said, it's not really something that I want to go over because it's not necessarily the most important thing. If it is something that you feel like you're worried that's going to come up on the test and whatnot, you can always ask any of your science teachers to teach you about it. Or if you head to BBC Bite Size and look at purification of copper, you can find some really wonderful resources there as well. Okay. Now, really quickly, what I want to do is I just want to give you a couple more examples before we end. And obviously, I'm going to get you guys to just work on them, and then I'll give you the answers afterwards. Okay. So you can pause the video just to copy this down, but I'm going to erase this really quick just to give you the practice problems. Okay. And I'll just kind of squeeze them in here. Okay. So what I'm going to do is I'm going to give you the compound that's going into the electrolysis mode or process, and I want you to tell me what's going to form at each of the electrodes, okay? Because that's a work in itself, and you might have to draw out these diagrams if you feel like you need to. But yeah, so the first compound is zinc chloride, which has a formula of ZnCl2. Second one is going to be copper sulfate. So copper sulfate. And I'm going to make a note here, which is really important. Copper sulfate is aqueous. So that I denote that by an AQ, and the formula for that is CuSO4. You're going to need to know that sulfate ion. And the last one is aluminium oxide. So this is actually one that we did in class, but it doesn't hurt to have that example again. So this one has the formula Al2O3. Okay. So let me just make sure that you understand this here. These two are molten salts. I'm just going to point you in the right direction. So look back at your notes for molten salts. This one is ionic solution. And that's why I put aqueous, which means that copper sulfate is actually mixed in with water. Okay, so what I want you to do is I want you to tell me, for if I put zinc chloride through electrolysis, you know that's going to form zinc and chlorine, but where are those going to be formed, right? So you have to tell me this is formed at the anode, this is formed at the cathode. Same thing for copper sulfate. You have to tell me what's formed at the anode and the cathode, except because it's an ionic solution, you have to tell me at each anode and cathode, you're going to have two ions. So which one of the copper and sulfate or hydrogen hydroxide, which one's going to form? Okay. And then last one, again, is a molten salt. So which one is going to be formed where? All right. So go ahead and solve those out. And then on the worksheet that I'm going to have posted on your class teams, you'll see the answers to these. Okay. Thank you guys for watching, and I hope to see you guys very soon.